Hello and welcome to our first video on 8.4. This one is about polar bonds and polar molecules. At the beginning of this section it talks about how snow covers about 23% of Earth's surface. Each snowflake is formed from as many as 100 snow crystals, and the size and shape of each crystal depends mainly on the air temperature and the amount of water vapor in the air at the time the snow crystals form. Now, what you're going to see is that polar bonds and water molecules have an influence on their basic shape. Why does water form crystals that make its solid form less dense than its liquid form? We can see that this is the case if we look at this picture in the upper right-hand corner. The liquid form shown on the left has molecules of water more closely spaced due to their disorganization than what we see in the crystalline form of the solid on the right. In order to understand why a substance has certain physical properties, it requires that we have an understanding of the bond types within the substance and the three-dimensional arrangement of the bonded particles, things such as the shape of the molecules. Now, not all bonds are the same. We've discussed how bonds can be broken down into three basic categories: ionic bonding, metallic bonding, and covalent bonding. But even when we're talking about covalent bonds, they're not all the same. Pictured here on the right, we see two different covalently bonded molecules. We see chlorine at the top, which is a molecular element, where two chlorine atoms bond to each other, and they both have an electronegativity value of 3, so there's no difference in electronegativity, and you see this molecular orbital shown in green that's symmetrical. It is a totally nonpolar bond because there is absolutely no electronegativity difference between two chlorine atoms. Now, in the bottom picture, we see hydrogen bound to chlorine. And there is a difference here. We see a difference of 0.9, and that difference is evident when we look at the molecular orbital formed as hydrogen bonds to chlorine. We see in the green region that it's centered more around the chlorine atom, and there's less of it down around the hydrogen atom. We see that this is a polar bond because of the difference of 0.9. And there are different amounts of polarity. So covalent bonds arise from sharing of electrons, but bonded atoms do not always share those electrons equally. Now, here's that chart of electronegativity values found on page 177 of your textbook. The difference in electronegativity values of bonded atoms is what we use to determine the type of bond. And if we're looking at a covalent bond with a difference between 0 and 1.9 in those electronegativity values, then we can even distinguish within covalent bonds, are they polar or nonpolar? Are some of these bonds more polar than others, etc. So a bond with an electronegativity difference of 0.5 really is not that much different. It's not that much more polar than a bond with a difference of only 0.4. But we had to have a place to cut it off. We like to be able to categorize things. So they made the cutoff value be 0.4 for the difference. So there's not really that big of a difference just because something with a difference of 0.4 is still classified as essentially nonpolar, and something with a difference of 0.5 and above is either polar, very polar, or ionic. They just have cutoff values that help us to classify them, to categorize them into these different ranges. So you need to remember that these cutoff values have been set by scientists to help you to compare attractions for electrons in a bond. So generally speaking, atoms that are nonpolar covalently bonded are considered to share electrons fairly equally, while polar covalently bonded atoms experience less equality in sharing. And ionic bonding is the extreme situation. It's such unequal sharing that the atoms are considered to have pretty much just transferred those electrons instead of sharing at all. Now, when chemists want to indicate that a bond is polar, they use an arrow pointing from the atom with the lower electronegativity value toward the atom with a higher electronegativity value. They even cross the arrow at its beginning as a reminder to the person looking at it that the electrons are being pulled away from that atom in the molecule. So that atom has a slight positive charge, and the atom towards which it's pointing has a slight negative charge. Now, you notice in this diagram in the upper right, we see boron trifluoride, and there's arrows superimposed upon those bonds, showing you that the difference in electronegativity between boron and fluorine is significant enough that you end up with the fluorines being slightly negative and the boron in the center slightly positive. Now, the way we show a slight positive or a slight negative charge is we use the Greek letter del. Kind of looks like a squiggly D. And that is followed by a positive or a negative symbol, depending upon whether it's a slightly positive or a slightly negative charge. If we look in this diagram in the lower right, we can see when we draw a boron trifluoride molecule, giving it its trigonal planar shape that it would have, we can draw arrows next to those bonds to indicate the polarity. Boron is a 2.0 value from that table. Fluorine has a 4.0 electronegativity value. So the difference is 2.0. These are highly polar, so polar that they are right onto the edge of the ionic bond realm. We put a cross across the beginning of those arrows in that diagram to indicate that the boron side on each of those bonds is slightly positive, and the fluorine side would be slightly negative. Now, if we consider HBr, pictured on the right here twice, in hydrogen bromide, there's only one bond. Since bromine has an electronegativity value of 2.8 and is more electronegative than hydrogen with a value of 2.1, we would draw an arrow that points towards bromine. The hydrogen end is slightly positive, so we'd put a del plus at that end, as you can see on the left side of this upper diagram. And we see a del minus next to the bromine because it's a slightly negative end. It has more of an attraction for the electrons in the bond, and therefore it's going to have those electrons pulled more towards that side of the molecular orbital. In this diagram, we can see that when we draw a structural diagram, it's pretty basic, but we can definitely see that there's a polar bond here because when we see the difference is 2.8 minus 2.1, that's a 0.9 difference, we know this is a polar bond. And so we do need to indicate that in our drawing by drawing this arrow next to the bond. It's going to point towards bromine because it's the more electronegative element. We've crossed the side that's close to hydrogen to make that end look more like a plus symbol to remind us that the hydrogen is the positive or slightly positive end. Let's try a couple more. Let's try water first. Now we know that water is a bent molecule, and this drawing would approximate its shape. When we look at this molecule, we can see that hydrogen and oxygen are bound together, so we have to look up their electronegativity values. Hydrogen has a value of 2.1 and oxygen is 3.5. Definitely a difference. We're going to need an arrow, and oxygen being the more electronegative of the two means that that arrow is going to have to point at the oxygen. We draw that against one bond, and we cross the end next to the hydrogen because that's the positive end of that bond. And we do the same thing for our other bond, crossing its end next to hydrogen as well. We would draw these arrows of the same length because the length is supposed to indicate something about the polarity, not just the direction, but the length is supposed to indicate the strength as well. Longer arrows usually indicate a higher polarity, a higher difference in electronegativity. So we do end up with polar bonds in the water molecule. Looking at carbon dioxide, we know that it's a linear molecule. Those double bonds get as far apart in space as possible, which is 180 degrees, making this linear. Now, when we look up carbon and oxygen, carbon has a value of 2.5 and oxygen 3.5 for their electronegativity values. That means they have a difference of 1.0. Having that much of a difference means they are polar bonds. Oxygen is the more electronegative, so the arrows would point towards those oxygens along each bond, as we see here. That's going to make the oxygen ends of that molecule to be slightly negative and the carbon middle to be slightly positive. Now we've been looking at bond polarity, but what about molecules as a whole? When a molecule contains polar bonds, it may also result in a polar molecule, meaning the molecule as a whole has a direction of polarity. We call that a dipole. A dipole has the word di in it because it has two poles. It has at least one end that's positive and one end that's negative, or at least slightly positive and slightly negative. So those we call the poles of the molecule. Now they need to be ends that are slightly positive and slightly negative. Not all molecules have at least one end positive and at least one end negative. Some may have all ends positive and a middle negative, or all ends negative and a middle positive. But we need to have ends where we have at least one end positive and one end negative to get a dipole, a polar molecule. So what's required for a polar molecule to exist? First of all, it must contain at least one polar bond. That's a must. If there's not even polar bonds, it's impossible for the molecule itself to be polar. Another thing that's required is if it does have at least one polar bond, then the polar bonds that exist in the molecule must not cancel each other out in terms of three-dimensional direction. So molecular shape is also going to be important when we're considering molecular polarity. Let's go back to boron trifluoride and determine if this molecule is polar. When we look at the molecule, we can see that all of the fluorine atoms are the three ends of this molecule. They all have a slightly negative charge, hence the del negative at their ends. And the middle, the boron in the center, is slightly positive. Now, this is a trigonal planar molecule. That central atom is right in the middle of a planar triangle. So that middle is not an end, which means there is no positive end on this molecule. There are only negative ends. Since all ends are negative, we cannot have a polar molecule here. You have to have at least one of each. Another way to look at whether this is polar or not is to do a vector addition. Add up those arrows that indicate the polarity of each of these bonds. Now we need to keep their direction and their length correct relative to each other if we're going to do it this way. And if I draw all three of those starting with one bond going up, and then one going to the side, and the third one going back the other direction, you'll see as I draw them, I end back where I began, which means there's no net polarity. If you go from the very beginning of the beginning arrow to the very end of the end arrow, you're at the same spot. So there is no net polarity to this molecule, even though it contains very strongly polar bonds, so polar that it's verging on ionic. If we look back at the hydrogen bromide molecule, this molecule consists of only two atoms and a single bond. There is no other polar bond to cancel it out. So this is going to have to be a polar molecule. And its polarity for the molecule would point, just as that bond does, from the hydrogen towards the bromine. What about carbon dioxide? Remember that it's a linear molecule, and its polarity of its bonds, both of those point towards the oxygens away from the carbon, making both of those oxygen ends slightly negative. The carbon is slightly positive, but once again, it's not an end. This molecule is linear, it's right in the middle. So there's no net molecular polarity. If we look at water, remember water is triatomic, like carbon dioxide, but it's not linear. It's a bent molecule. So because it's bent, oxygen is another end. It's not stuck right in the middle between two hydrogens. It's out there sticking out in another corner. So when we look at these polar bonds, both of them pointing from hydrogen towards the oxygen, as we can see in this lower picture, we can see that we end up with the oxygen end slightly negative and the hydrogen ends, both of them slightly positive. So out to the right side here, you see another arrow drawn that represents the molecular polarity. Overall, there is a slight polarity going from the hydrogen end towards the oxygen end, as shown here. And this is a good spot for us to stop for this first part of the lecture, and we'll pick up in the next slide on part 2 of this same lecture.